We'll now look at arbitrary products. Okay, so infinite products, X alpha, we have a collection of topological spaces. Now, since this tends to look unnatural, we'll in parallel have examples x1 cross x2 and so on. Infinite products, so that is to say A is the natural numbers. Okay, so we take positive integers as the indexing set and have this as an example. Formally, this is not going to be very different yet. So eventually, countability will matter. So you have to think of arbitrary collections. And let's look at this. So now we have two choices. So we have two choices, and we take a product topology, which is in the correct generalization of the finite case, and box topology. Now what we mean by correct is that we have the right amount of continuous functions. After all, the topology must have the correct behavior. We will see in various senses why the product is the correct product. So box topology is simply naively that we are given U alpha contained in X alpha and take basis as the products of U alpha. Okay, so for example, you would have U1 cross U2 cross UN cross so on. Okay, and then these things, so of course in both cases this is to be open, this is in Xn, so this is open, and so here, so this is open sets. The products of open sets, arbitrary ones. So this is called box topology. We will only see it enough to see why it's the wrong choice. Product topology, instead we abstract the property of the product topology in the finite case, and the key property is the projection maps are continuous, and that's all in a sense. So this is initial topology such that P alpha, which I'll define in a moment, are continuous. And we can have other characterizations as well, as we will see. So now we'll leave this aside and focus on the product topology. So this is on the set, which is going to be the set of all, we can think of them as sequences X alpha with alpha in A, okay, indexed by this, and such that little x alpha is in the space X alpha. So you have tuples indexed by elements in A, so that X alpha is in alpha. So as in the example, there will be tuples x1, x2, etc., but infinite tuples. Xi is in capital Xi. Okay, so especially in this case. And so now what do we have? We have projection functions first of all, and we'll figure out what is the initial topology there. So okay, so we have P alpha, which will map. So this set is also going to be called product. We'll use the usual abuse of notation X alpha. Okay, so this is a map from alpha in A of X alpha, and this maps it to let's call it P beta, because alpha is the rotating index. So P beta, this maps to X beta, and this is of course the map which will take X alpha, this tuple alpha in A, to just the single element X beta. So in the example case, we have Pn will map x1, x2, etc. to just the nth coordinate. So these are the coordinate functions. Okay, so well, what does it take for these to be continuous? If P beta are continuous, okay, so for U beta contained in X alpha, X beta, of course, U beta, P beta inverse of U beta is equal to, is open. Okay, so what is this equal to? So P beta inverse of U beta is going to be the set of all X tuples X beta X alpha alpha in A of and with little x alpha in X alpha, but also with the property that X beta belongs to U beta. First one is also true, it's a further subset. Okay, so okay, let me not write that part as an example. We'll write the next step as an example. So you can think of this as product of alpha in A of various sets. Okay, so let's call them Z alpha, where Z alpha equals, in the special case where alpha is beta, it's going to be U beta, and it's going to be all of X alpha otherwise, if alpha is not beta. Okay, that in this example is going to be, suppose n is not 1, I mean it's going to be x1 cross x2 cross so and so, except we have a un cross x cross x, whatever it is, capital N onwards. So everything is the full space except one ui. So all these sets have to be open. Okay, this should remind you of the subbasis we saw in the finite case. Okay, and now furthermore, now if we take intersections of these, we get more. Okay, namely, so suppose we fix alpha 1 alpha n and u1 can, so these are distinct in a they're all distinct, and then we take u alpha 1 u alpha I contained in X alpha I open. Okay, then let's look at the intersection of I equals 1 to n of P alpha I inverse of U alpha I. So this must be open. Okay, so then this is open. Well, what is this? This is again now the product of beta in I'll call that, I've been calling the index alpha in A of again Z alpha, where Z alpha is going to be equal to U alpha I if alpha is alpha I for some I equals 1 to n. They're distinct, so at most 1, and X alpha otherwise. So if it fails to be one of these, it falls by default to X alpha. So these are the products of these, and so we are looking at such sets. So the product topology. The product topology. Okay, so I'll first say these form a basis for a topology. Needs a little verification. I'm calling it an exercise. There's not much is gained by my writing out the details. So there are two ways in which this intersection can happen. You could have, so if I have an intersection of sets and then another intersection of sets of this form, okay, of Z alphas. So then there are two kinds of things that can happen. So either you have extra indices or you have an overlapping index. Okay, so maybe let's look at some details, namely given these form a basis. Okay, so it's worth actually explicitly writing out what this is. That is, B is product of alpha in A Z alpha, where Z alpha is contained in X alpha is open for all alpha, and so the specific indices are not are here in the construction, but when I'm looking at the product, I don't have to specify them. What I have to specify is there are only finitely many. So Z alpha equals X alpha for all but finitely many alpha. Okay, and so these form a basis for a topology. So if I look at intersection of finitely many, So if I have finitely many, so if let's look at finite intersections. So if I take intersection of products alpha in A of, let's say, Z alpha I equals 1 to some little m, is product alpha in A of this intersection Z alpha I. Okay. So this is I equals 1 to little m. Okay, so what do we know about this? So this is open in X alpha, and so this is this product, and for all but finitely many alpha, well, what happens? The exceptional cases where Z alpha is not X alpha are only finitely many for each I. So you put together finite collection of finite, it is still finite. So Z alpha I is X alpha for all I. And so intersection I equals 1 to m of Z alpha I is going to be X alpha. Okay. So thus this product is actually in B. Intersection I equals 1 to m. Z alpha I is in B. Okay, so we have many nice things. So what did we start off by saying? We said we wanted to find the coarse topology, the initial topology given by all projections being continuous. And when we look at these, so I will give the colored form of this with indices. We look at basic sets by looking at subsets, open subsets in X alpha, and pull back one projection. So that will give you an open set. And we intersect finitely many, we'll get an open set. And these finitely many are products, but not arbitrary products. All but finitely many are going to be the whole space. Okay. So in the case of I equals n, your B will be the set of all products, which will be Z1 cross Z2 cross Zn onwards, with Zi equals Xi for all but finitely many. Many i's, and also Zi in Xi is open in all cases, including of course where it is all of Xi. So this is the case, and when we intersect finite collection of these, then in all but finitely many, that is excluding those which in one of the terms of the intersection has Zi not being Xi, the intersection will be still all of Xi. So this somewhat abstract construction gives us product topology, but we see it's quite concrete. So it's the initial topology, but it is product, except that we have product with finite support in a sense. Okay, so we have these. Now let's see one more property of this, somewhat sharpening being the initial topology. Okay, so namely, if I have F, so let take another Y be a topological space. And F from Y to product alpha in A of X alpha. So suppose, and F is such a function, so be a map. Okay. Then F is continuous if and only if F composed with, it has to go the other way. We have F and then we apply P alpha. So it's P alpha composed with F. This maps Y to X alpha is continuous for all alpha in A. Okay. So we'll get to the proof, but let's first see remarks. So F of Y is f alpha of y, alpha in A, where so f of y is this tuple, f alpha of y, alpha in A, where f alpha is just p alpha composed with f. So the projections determine this as a function. Okay, so this is an element in the product, alpha in A of x alpha. So the continuity is also determined by these. So f is determined by these projection functions, and they are essentially the coordinates. Okay, so this becomes clearer in the special case. F of y is going to be f1 of y, f2 of y, etc. It's going to be an n tuple like this, where fn of y is pn composed with f of y. So the nth component, which is the projection. Okay, so that makes the statement more natural. I'll also comment is by the above, p alpha inverse of u alpha. If I look at this set where u alpha is contained in x alpha open and alpha is in A, this is a sub-basis for the topology. Indeed, we looked at these sets, saw that they were open, looked at their finite intersections and declared that to be the basis. So by construction, this is a sub-basis for the topology. And so now the proof is kind of clear, which is that if f is continuous, as p alpha is continuous, you have a composition. This p alpha. Yeah. So conversely, enough to show that f inverse of w is open for a sub-basic open set W. So what is this sub-basic open set W? But that's because if you have an inverse image being open for sub-basic intersections, then by taking finite intersections, it's true for basic, and then by taking unions, it's true for all open sets. This we had proved. But a sub-basic set for our favorite sub-basis as above is W is P alpha inverse of U alpha. Therefore, F inverse of W is P alpha inverse, F inverse of P alpha inverse of U alpha, which is just F composed with, compositions flip, which is P alpha composed with F inverse of U alpha, which is open, because this guy is open, as P alpha composed with F is continuous. So the converse is if each composition with a projection is open. So at the level of sets, a product is determined by knowing all its components, but as a topological space, if all the components are continuous, then the function is continuous, and conversely. So this makes product topology very nice. We will see this in a more abstract sense even with what are called universal properties. So there are two things left to see. One is what is good about the product topology in an even more abstract sense, what are called universal properties, and what is bad about the box topology, both of which we will see in the next segment.